My name is Mark Sale. I am Vice President in the Integrated Drug Development Group at Certara, and I'll be joined by James Craig, who has been the Principal Software Engineer on the PyDarwin project. We're going to be talking about PyDarwin. PyDarwin is an open source all Python solution for model selection in non-mem. It is in the public domain. The URL for the GitHub repo is listed there. And it's been developed under a grant from and in collaboration with the Food and Drug Administration. There have been other applications for automated model development in non-mem. We believe, though, that we have developed a completely general solution. Literally anything you can think of that you might want to search for in non-mem, you can code and do a formal machine learning-based search using PyDarwin. There are currently 6 model selection search algorithms available. These include exhaustive search, Bayesian optimization or Gaussian process, random forest with gradient boosting, genetic algorithm, and particle swarm optimization. Again, there have been existing automated methods for model selections, including the well-known stepwise covariate modeling available in PSN, the Wald approximation, the newer co-search in the PharmPy package, as well as a lot of artificial intelligence machine learning methods for sorting through output files looking for relationships between covariates and parameters. All those are currently limited to covariate search. There have been at least one other approach to full model development, including the automated model development currently available in PharmPy. But we're going to be talking about PyDarwin. Again, the key strength of PyDarwin is that it's not limited to covariate search. It is a true global search, searching for compartments, error models, residual models, absorption models, initial estimates for parameters. Anything that you can imagine coding non-mem, you can search for. The reason to use it is primarily because it's more efficient, at least more efficient in terms of human effort. This all happens in the background, highly parallelized, running 24/7. And so the actual clock time is going to be shorter, as well as certainly the human effort required to develop these models is going to be much, much less. We also have demonstrated that it's more robust. There are some fundamental flaws in the way we currently develop these models. And we think that we've shown that this is a more robust approach to model selection. It also avoids any potential bias going into the analysis about whether this molecule is eliminated, has linear elimination route, or whether there are any specific covariates that should influence the outcome. It is an objective, strictly numerical search of the parameter space looking for the optimal model. Importantly, it provides an opportunity to really examine the full problem, things that you wouldn't have the opportunity to think about earlier, unanticipated covariates, multiple initial estimates, a number of things that are difficult to find the time to fit into a timeline for a traditional analysis. This build automatically will search for them in a very efficient and robust way. Central to the concept of identifying an optimal model is the model search space. And all the algorithms available in PyDarwin use the same definition of the search space. And in some ways, this search space is analogous to the parameter search space that non-mem uses, along with Monolix or NLME. On the left is a diagram of a very simple search space for the parameters, with volume on the x-axis and clearance on the y-axis. And on the z-axis is minus twice the log likelihood. And all non-mem does is it searches for the optimal value of these two parameters, volume and clearance, that minimizes the value of minus twice the log likelihood. The analogy for a model search in PyDarwin, in this case, another simple two-dimensional search space with a number of compartments on the x-axis and the elimination mechanism on the y-axis. Now, on the vertical axis is a quantity we're going to call fitness. Again, a numerical quantity. And so very analogous to minus twice the log likelihood that non-mem optimizes on, we're going to optimize on the fitness. There are important differences between the search space for non-mem and the search space for pi-Darwin. Non-mem is a continuous search space, so there is a derivative. And the FO and the FOCE methods use this derivative to look for the downhill direction and then walk in the downhill direction until it doesn't get better anymore. And then it concludes that it's found the minimum value for the objective function. The model search space for pi-Darwin, in contrast, is a categorical or discrete parameters. There are no derivatives. It's either one compartment or a two compartment. It's not a 1.43 compartment model. So the algorithm has to be different. In fact, the algorithms are more complicated. There's a number of them available, as there are a number of algorithms available for parameter estimation in non-mem. So we're looking for the optimal combination of these discrete values that result in minimizing some number. In this search space, a search space consisting of many dimensions, each dimension requiring the selection of exactly one value. For example, there might be a dimension for the number of compartments, where there be a value of 1 or 2 or 3. Again, not 1.43, but discrete categorical values. There are elimination options, linear or Michaelis-Menten, or perhaps target-mediated drug disposition. There could be a dimension for the absorption options, linear, zero-order, transit compartments with or without lag time, and then the covariates, all the possible combinations of interest, defining relationships between covariates and parameters. Residual error models, additive, proportional, combined, and the omega structure, which parameters have between subject variability, as well as the off-diagonal elements of the omega matrix. And finally, again, importantly, I think searching for initial estimates, something that's probably overlooked because it's tends to be time-consuming. This global search algorithm can include searching for initial estimates. The problem with the search space definition is that it becomes very large very quickly. A fairly modest search, the number of 3 compartments, 1, 2, or 3 options for the elimination mechanism, 6 options perhaps for the absorption, different combination of zero-order, first-order lag time. There's different residual models between subject variability terms, covariates, etc. You end up with 700,000 possible models among all of these. Clearly not something that we're going to be able to manually write code for and evaluate. And so we evaluate that by defining this search space as a string of numbers, with one number corresponding to each dimension in the search space. In the case of genetic algorithm, those numbers, integer values, 1 or 2 or 3, get mapped to bit strings. In this case, for example, the first 2 bits, this 0 or 1, defines the gene for the number of compartments, and the values in that gene map to the specific structural model in non-mem. For example, 0, 0 might map to a 1-compartment model. 0, 1 maps to a 2-compartment with K23 and K32, 1, 0 to 2-compartment with Q and steady-state volume, and 1, 1 to a 2-compartment with Q and the peripheral volume. That mapping then corresponds to code that gets dropped into a template file and results in a syntactically correct non-mem control file, which is then run. The output from that control file, this fitness function that we've mentioned, is then used to feed back to selecting a set of models to explore next. The exact method for making that selection for the next group of models to examine depends on which algorithm is chosen. Genetic algorithm uses a series of operators like crossover and mutation to select the next generation, and other algorithms use different methods. Importantly, pi-Darwin handles all this internally. You don't have to worry about the bit string or the integer string or how it gets mapped. All you have to do is provide a list of options that you want to explore for each dimension. All of these algorithms in the machine learning phase are global search algorithms, and global search algorithms require a series of assumptions, generally simplifying assumptions. For example, Bayesian optimization makes an assumption about a multivariate normal distribution, a nice smooth distribution. Those of us who have been doing this for a long time recognize that not uncommonly, the relationship between the model and the fitness or the goodness of the model is not as smooth as we might think. Small changes in the model can result in significant changes in how good the model is. Sometimes just whether it converges or whether it's a successful covariance step, but also small changes can result in significant improvements in the objective function. The result of this is this multivariate probability, smooth probability distribution is frequently violated, that these search spaces are not as simple as we would like them to be. And so these shortcuts, these assumptions that these algorithms make can lead to a problem. What we found is that we can combine these global search algorithms with a local search much like we do manually, where you make one or two small changes at a time, and you see whether it made the model any better. And if it did, you keep it. If it didn't make it better, you discard it and try something else. And then we combine that more thorough local search with a global search for generally good models, we can end up with a very robust solution, basically combining exploration using the machine learning approach, looking at generally good models, and exploitation using what we found about this region of the search space looks pretty good, exploiting that and trying smaller changes in a local region. Unfortunately, we also found that making one change at a time in this local search is not adequate. It's not uncommon that all single changes in the control file will result in worse models, but there are some combinations of changes, making two changes at once, that result in a better model. And that again gets back to just how complex this search space is and how unpredictable the search space is and how not smooth it is. And so we've added an option for a 2-bit local search where you make all possible 2-bit changes, all possible changes in pairs to the model. The downside of that is it's fairly computationally intensive, with the number of models being n squared minus n divided by 2, where n is the number of bits in the bit string, number of dimensions. We talked about this fitness function, this search criteria before. It basically gets down to what do we think is a good model? What are we looking for in terms of the performance characteristics of the model? In PyDarwin, it can be user-defined, and it's quite general. It starts with minus twice the log likelihood, the output from non-mem or NLME, and then it adds penalties. It adds penalties for all the things that we typically like to see in a, quote, good model. We like parsimonious models. Typically, we would add 3.84 points to the objective function for each estimated parameter at p less than 0.05. We like models that converge. We think the models that converge are probably better than models that fail to converge, and so we add a penalty for that, for models that fail to converge. Similarly, for a covariance step, if you want a successful covariance step, you can add a penalty for that that will then drive the search toward models that have a successful covariance step. Same for correlation task, condition number. And finally, there's an option for including user-defined R code. A key component of evaluating the goodness of a model is diagnostic plots. And we use diagnostic plots when the standard non-mem output doesn't really capture what we're looking for. For example, most models are the objective function, minus twice log likelihood, is relatively insensitive to the Cmax because most of these models have residual errors that are proportional to the predicted value. The predicted value is Cmax high, and so it's fairly insensitive to that. It's happy to ignore significant bias in Cmax in order to get other points better estimated. But if you want a model that captures Cmax adequately, you can add R code that adds an additional penalty for bias in Cmax, sort of like a posterior predictive check, where one simply takes the predicted or the simulated value for Cmax and compares that to the observed value and then adds the penalty based on the bias in that estimate. The downside of the command line version of PyDarwin is that it's fairly cumbersome. There are 3 required files. 2 of them are shown here. On the left is the template file, which you'll recognize looks a lot like a non-mem control file, except there are these strings, the curly brace advan square brace 1, and down here, curly brace advan square brace 2. These are referred to as tokens, and they are little text strings that can be swapped out for text strings defined in the tokens file, resulting in different non-mem control files and different models. For example, the advan1, the advan token group, defines whether this is a 1-compartment or a 2-compartment model. If it's a 1-compartment model, then this text, advan2, gets substituted in here in the $subroutines record, and then no text is required for initial estimates for K12, K21, and similarly no text for initial estimates. Whereas if you want a 2-compartment model, you would put advan4 in here in place of this token, and you then would need to provide initial estimates for K23 and K32 in the $PK block and initial estimates in the $theta block. The downside of this is these files, the token files in particular, are fairly difficult to work with. This is a JSON format file. All the curly braces and square braces and quotation marks and commas and everything else is fairly rigidly formatted, and it ignores white space. And so if you want a new line, as we frequently do in non-mem control files, you have to add the \n to generate a new line. Usable, very robust, very general, but fairly difficult to use. We just released the latest version of PyDarwin, version 2.0. The important addition to this is support for NLME, not only a mixed effect package and an R package for setup and execution for NLME models using some user-friendly R functions. And that URL is given here to download that public repo. We also just got published a tutorial on PyDarwin. The EPUB URL is listed there in CPT, and the print version will be coming out sometime in early 2024. Because the command line version of PyDarwin is quite cumbersome to use, we have developed a graphical user interface around our non-mem workspace called Pirana. It provides a graphical user interface that is really almost entirely drop-down menu checkbox that generates these 3 required files, and also provides tools for report shells, graphics, and a lot of other diagnostic plots that James will be talking about after we do a quick demo of the Darwin in Pirana. So now we're going to actually construct a fairly simple analysis model search space based on a fairly simple data set. This is the Pirana interface, and in Pirana there are a number of options for what kind of a model you're running. Selected here in the upper right, there's the .mod file, standard non-mem control file, a scan file, but we're going to do a Darwin file. So we'll select that and then go to New Model. And this opens up a browser. The interface for defining the model is written in JavaScript and opens up in whatever standard browser you're using. You start with a data set. You're on the left, and we'll search for data set. We have a simple data set here that opens up, and this gives you all of the available data items in a list box on the left. And we'll click the auto here at the bottom, which then recognizes the default non-mem input variables like ID and time and amount and dB. And that leaves the covariates. And we're going to add weight and creatinine clearance as continuous covariates, and then sex as a categorical covariate. And this completes defining the data set And we'll move on to the model template options. The model template options define the basic structure of the model. In this case, we're going to be looking at a 1 and 2 compartment model with first order absorption. And we'll include all the covariates that we have selected, sex, weight, and creatinine clearance, in the model that can be searched for. That opens up these two tabs below here, one for admin2 and one for admin4 parameters. On admin2 in non-mem, there are 3 required parameters: clearance, Ka, and volume. And those all need to be present. They're not optional. They must be present in all models that will be generated by Pirana. And we'll provide an initial estimate of 0.1 for clearance and 0.5 for the volume distribution. Then there are lots of optional parameters, and this is where one defines a search space. For example, we are going to be searching for whether or not the data support a absorption lag time for doses in the compartment 1. So the options here are none, present, and searched. None meaning that they will be in none of the candidate models. Present meaning they will be in all the candidate models, like the required parameters are. And searched means that it will generate a dimension in the search space to search whether or not those, including the absorption lag time in the model, improves the fitness. My initial estimate for that is 0.2. Similarly, the omegas are always optional. You're required to have at least one, so we will say that the between subject variability is always present on clearance, but everything else we're going to search for. And we use the default initial estimate of 0.3. So this now defines a 4-dimensional search space. One dimension is the presence or absence of the absorption lag time, and the others are the between subject variability present or absent on Ka, V, and absorption lag time. We'll do the same for admin4. Now there are 5 required parameters, and we'll give initial estimates for those. Mostly use the default values. And similarly, we will search for presence or absence of an absorption lag time with also an initial estimate of 0.2. And same for the between subject variability terms. Always present on clearance, but everything else will be searched. So now we've added 2 more dimensions, the between subject variability on the Ka and volume will overlap with that was used for the admin2 model, and similarly for the ALAX, we've added 2 new dimensions to the search space for Q and for V3. We're now up to 6 dimensions in the search space. Once you've defined the basic structural model and between subject variability search, you can look at the covariate search. The covariate search dialog includes an option for every combination of parameters and covariates that you included. And we included three covariates: creatinine clearance, sex, and weight. The default for them is none, meaning they won't be included, they won't be searched for. But if you do want to search for example, clearance as a function of creatinine clearance, you just change that none to searched. Use the default initial estimate, we'll do a power model. And for sex, we'll search for that as well, but do an exponential model. Sorry, we're actually not going to search for this. Clearance as a function of weight, we'll search for that with a power model with an exponential. With the power model with the allometric parameter of 0.75. Ka will search just for sex. And Q, we will search for sex and as an exponential model, and weight as a power model. It's going to 0.75 again. V2, sex, exponential model, and search for volume again. V3 again, sex and weight. And we won't do anything with the absorption that time. Won't look for any parameters on that. And that completes the parameter definition for both Advent1 and Advent2. You see all of the parameters for both models are present here at Q and B3. The next step is the template extras. Here are the non-mem options, like the algorithm for minimization is selected. In this case, we'll use the default conditional with interaction method. And the covariance step will be an unconditional print equals E, so we'll include the eigenvalues for that. We'll also include table output for making diagnostic plots. This is standard exposed table output, and including the continuous covariates of weight and creatinine clearance and the categorical covariate of sex. The sigma search space includes just the initial estimates, and there are default initial estimates in that which will work for this model. We'll also use the default penalties. The default penalty for each estimated parameter is 10 points for theta, omega, and for sigma. We also like the model to converge, and so at a fairly large penalty of 100 points added to all models that don't converge. This will push the model selection algorithm strongly toward models that do converge. Similarly, for the covariance step and the correlation matrix step test and the condition number test, all with a penalty of 100 points. We'll also include a very small penalty for a model that has tokens that do not influence the control file. You'll recall there was a search for between subject variability on Q. Well, if the model is Advent2, there is no Q. And so any search on the inclusion of a between subject variability term on Q will have no influence. There is no Q, so there is no between subject variability on Q. We had a very small penalty just for simplicity. It actually doesn't impact the control file. The control file will be correct. It won't include an omega term for that, but we'd still prefer that it not be there. And so we had a very small penalty for that to drive the model to removing those whenever possible. We also need to provide a value for models that crashed. The non-mem models will crash, they always do. And you need to provide a crash value for the algorithm for any models that crash, and this number should be larger than any anticipated fitness value. We won't do any post-processing. That's not covered in this tutorial, but there, again, is an option for including an R script or Python code to be run after each model to provide a user-defined penalty for bias in Cmax or relative standard errors or post-hoc p-values for ADAs. Anything that the user wants to define. And finally, the model selection algorithm. We'll use a genetic algorithm with 5 generations and 15 models per generation. These are the default values, but in general, they should be larger. Typically, you probably want at least about 10 generations and probably 80 to 100 models per generation. We'll include a random seed, and we'll copy the same random seed we used before so we get the same results. There will be a downhill step at the end. We will not run it periodically just in the interest of time, and this is a very simple analysis. But we will run the downhill step 1 and 2 bit at the end. We'll include 2 niches. Niches are a penalty added to models when they become too similar to other models in the current population. This prevents premature convergence of the search around some small number of models and maintains diversity in the population. The niche radius is how similar other models need to be in order to incur that niche penalty. We'll use all the default values for the GA setup. We'll do carryover 4 models to the next generation. This is a function called elitism, where you preserve the 4 best models and carry them over to the next generation regardless of anything. They're not sampled. Those models aren't resampled. And all the other default parameters. You go ahead and save this model, and this will write it back to the Pirana environment so we can exit. the browser, refresh this, and there's our model. And we just run the model. Give it a name, and directly for the name to the directory that it runs in. And this actually writes the three files that we discussed: the template file, the tokens file, and the options file. And this is and then runs them at the command line. This is the output from that command line, initially just printing out the different options that you used. And importantly, the three directories that it uses: the temp directory, where non-members actually run; the working directory, where it keeps many of the files it's working with; and then the output directory. The output directory is where the final best model will be run, and the key models will be in the key models directory. And this starts running these non-mem files. It initially generates a random population of 15 models, and it runs them. Let that run for a few minutes. It does print out the fitness for each model, as well as capturing any messages that come from NMTran as this message, and then any errors that come from the non-mem execution. So after it runs the first generation, it then uses the genetic algorithm method to select a new population to be run. It lists the best model in this current generation, which you see has a fitness value of 200.6396. And then it gives you a very rough estimate of how long this is going to take. We really don't know how long it's going to take, because the downhill steps continue to run until it doesn't find a better model. But it gives you some rough idea, and it says that this will take another 59 minutes. For the second generation, you see that it copied over those four best models. Those were models 7 to 11 and 15 from the previous generation, and those, again, are copied over unchanged. It doesn't rerun them, because it already knows what the outcome of those models are, but then the remaining 11 models in this generation are new models, and so it runs those and prints out the output. After the second generation, you see that the best model hasn't changed. It's still 200.6396. So it gives you a message that there's no change in fitness for two generations. This will become how long it has run without any improvement will become an important criteria for deciding when the model has finished. Much like in the non-mem parameter estimation, it's done when it can't find anything better. But it takes a while for it to figure out whether there is anything better. In fact, in this application, we can go back to Pirana and click this button for Darwin Reporter, and that will start our Shiny app. And we'll start to see some basic diagnostic plots of how this analysis is going. So this is the current state of the analysis. It's finished 3 generations. And this plot on the left is a key plot for thinking about whether the model has converged yet or not. And we see that it had the best model in the dark purple line hasn't changed in 3 generations. It's still that same value of 200.6396. And there's only one key model so far. And this was the model from generation 1, model 7. So we'll close this and go back to Pirana. And we'll just let this run. Now it says it's going to take another 64 minutes for this to run. And now I'll just let this run, and I will sign off and turn this over to James, who will then show you the final diagnostics and the other tools for reporting and diagnostic plots. James?
All right, thank you, Mark. So I've already run the search to completion, same data set as Mark with similar setup options in terms of the search space. Before I show the Darwin Reporter application with the full search results, I just want to explore a little bit of the output here within Pirana. So you see, when I ran the search, we now have this Darwin Cert 01 folder that was been created. In this folder, we have three subfolders. So the key models folder, the output folder, and the temp folder. We also have various files here at the root of this folder. One file that you may be particularly interested in is the messages.txt. So this is the console output that Mark just showed in the terminal. So you can see full output here is saved to this file, messages.txt, and is available to inspect after your search. Some other important files to note inside the output folder is this results.csv file. So this results.csv file essentially is a complete overview of kind of the run record, right? Starting with the iteration number, location of the different candidate models in that iteration, fitness, model binary code, objective function value. So just, kind of a lot of just overall metrics from the entire search. But all this is certainly easier to visualize within an interface. And the Darwin Reporter interface makes all of that information available to inspect from the GUI. So you'll see here as I launch this, I'm going to hit run. And it's going to first create this Darwin data object, which is a structured S3 class based on all that run output information. Then it's going to import the exposed data, so all of our tables that we created for the candidate models, into a nice class that the Darwin Reporter application can interface with. And you'll see what I mean here. So just launch the application. You can see some high-level metrics about the number of models in the search space, number of models considered, models run in the search, number of models to best model, the time to best model, and then the overall search time. So all of our key models here are available in this key models table below. You can see the corresponding fitness value, the objective function value, and the different penalties that were added to the objective function value to obtain this fitness value. All these plots can be popped out. You can inspect them visually. Different options for interactivity and zooming in, etc. Same thing on the fitness penalties versus iteration. If you wanted to just look at O of V, you can toggle the penalties on and off, or conversely, just look at the distribution of penalties across the iterations and how these values decreased from the initial iteration to the final iteration. So next thing I'd like to do is maybe generate some model diagnostic plots and tables for the individual key models here in the search. So what I'm going to do is click this hamburger menu in the top left corner. Go to this interface. The first plots I'll be interested in, maybe those same exact plots that we just saw, right? So now I want to, there was some interactive exploration of those plots in the previous page, but now I want to customize these plots potentially, edit some color aesthetics, but more importantly, save these to go inside a report. So different options to edit, customization of the plot, legend position, line types, etc. Tons of display options, subtitles, font size, colors, face, etc. I'm just going to leave everything default for now, but I am going to tag this plot. So you'll see what happens here in the bottom right corner when I hit this big tag button. It's going to prompt us to give it a name. By default, it will just be the name of the plot. So, which is fine for my purpose. I'm just going to hit tag, and we're going to do that for a few different plots here. So we'll do our penalties versus iteration plot. We can also generate tables from this interface. So here's just an overall key models table that potentially I'd like to include in a report that has all the key models, what iteration each one of those key models was found at, and then the corresponding fitness value, OFE, and different other metrics. So I'm going to tag this plot, or excuse me, this table. All right, next thing is let's actually go to some goodness of fit plots for the individual key models. So I selected this basic GOF node and scroll down to the CW-Res versus PRED plot. When I click this plot, you could see that the key models here actually are available to select. So here's our first key model. I can toggle between different key models and see the same plot, right? Different, easily explored different key models with the same plot selected. You can tag these just like we did previously for any one of our key models. Let's say maybe on DV versus IVAR, DV versus PRED. All right, so I'm kind of going wild here, tagging a bunch of diagnostics that potentially I'd want to include in the final report. Covariate models, right? So we do have covariates in this search space. So I can look at ADAs versus covariate. Here we have our final model selected here. Here's sex versus our ADAs. I can change the covariate. Here I'll select weight, in which case we'll have a scatter plot, whereas for the categorical covariates, we saw we had a box plot. All right, so tons of different goodness of fit plots that can be generated from this interface, even individual tables for parameter estimates. So here, if we want our theta table, for example, I can click theta and go ahead and tag this theta table. All right, so I've tagged a bunch of plots and tables here. One other thing I do want to just show you quickly, some of the nice kind of interaction between the previous screen with any plot or table selected here. You can always go back to the search overview. Well, firstly, you can click this model file button and actually view the control file for a given key model if you want to get a feel for the structure and the covariates included in this model. But you can also just click this plot button, in which case it will toggle back to the goodness of the model diagnostic plots and tables interface with that key model that you just selected in the previous page automatically populated here, and the corresponding plots or table automatically available. So that's just some nice interactivity between the two pages. All right, so I tagged quite a few plots. I'm going to click this tag tab now. You can see the names for the tag diagnostics are all stated here in this list. I can toggle between any one of the tag diagnostics. But what's really helpful is it generates the underlying R code if I wanted to reproduce the same plot from the GUI, right, or make any changes from command line. So this tool can both serve as a quick, efficient way to report model diagnostic plots and tables, but also as a learning heuristic, right? So there's thousands of potential options that could be explicitly given inside this code in terms of customization with ggplot. So when we tie that back to GUI inputs, that clicking a box, changing some options in the GUI automatically gets translated to the resulting option in the corresponding ggplot or expose code. So with my tagged diagnostic plots and tables, now I'm going to click the report tab and put all those plots and tables in a nice report. So how would I do that? Well, first I want to decide, do I want an HTML, PDF, or docx report? I'll just do HTML first. Call this my report. I'm going to select auto format here. If I uncheck auto format, any one of those tag diagnostics, I could individually add them into the report output. Right? If I only wanted a subset of these, I can order these however I'd wish as well, in terms of how I want them to appear in the report. But the auto format, you can potentially, you'll have many key models, dozens of different tag diagnostics here. Could be a little bit difficult arranging those in a certain way. So with the auto format selected, it's going to intelligently add those into this report. Um, starting with the Darwin search plots, starting with any plots that you've tagged for your uh, early key models, all the way through your final best model, right? So I'm going to hit download report now. You'll see we get this message rendering my report.html. I'll let that finish. And I'm also going to generate a docx report. So do that. Download this report in docx. So we can kind of look at the differences between the two output. And what's going on under the hood here is we're using R Markdown. So all those tag diagnostics that we've saved essentially are getting added into this R Markdown report and then getting rendered into the corresponding output format that we've selected. All right, so I've generated my reports. I could leave this open or just close it, go back to Pirana. So I'm just going to do that now. If I wanted to save any of those customization options for my plots, I can save settings. All right, so now back to Pirana. Anytime that we create a report from this interface in Pirana, we can go to the Reports tab, and you'll see this shiny node appears. And I see I have this My Report. All right, so this is the same report that was saved in Pirana, or excuse me, in the shiny interface. And it's a nice kind of, really presentable HTML report about an overview of the search, the different penalties that went into the fitness function. Here we have our our fitness penalties by iteration plots, box plot. Then we have our mean and fitness and minimum cumulative fitness by iteration below. Here we have our key models table, and then the different plots that we've tagged for our key models all the way to our final model here, kind of nicely displayed in this report. And then I included the appendix in the report output. So when we include the appendix, it will additionally provide all the control files for each one of the key models here. So we can see what this also looks like as a Word document. All right, so we have our table of contents, our different sections, headers. So the neat thing about this is all based in R Markdown. So this can all be edited and customized right from the command line. In the Shiny interface in Darwin Reporter, I could download the report, which I did, but I could also download the raw R Markdown, right? If I wanted to bring this back into RStudio, make any changes, add any additional text into my report. But the important thing is the plots, right, are already generated, and those, you don't have to, regenerate or execute the code for the plots again. So it provides a lot of efficiency here in your workflows. All right, one other thing I do want to show is some new integration of a VPC application or PSN VPC output. So I'm going to go ahead and just click into that Darwin Search 01 folder that contains my results. So we can click into the key models folder. Just like, we use the Darwin Reporter interface, which provided a little bit more efficient mechanism to kind of wrangle all this Darwin output data in a single interface and create a report and different plots, tables from that. Well, we can always navigate into the individual folders for the key models. So as you'll see here, I'm still in the Darwin extension. Now I'm going to toggle to mod. And here's my non-mem control file, right? I have my output files here. I can preview this file. I can make any changes if I want to duplicate this model, re-execute it, work with any of the scripts inside Pirana, view estimates, whatever it may be. So that's why Pirana, the kind of structure of Pirana provides a nice mechanism to navigate the Darwin search output. So the two applications really do work well together. I'm going to go to the final best model selected in the Darwin search here. I'm going to click this model. So I want to create a VPC for this final best model. So what would I do next? Well, here we just have the control file for the final best model, not the control file with the final parameter estimates. So we can go ahead and duplicate this first. Go to right click, model. We'll go to file actions, duplicate. I'm going to click use final parameter estimates from reference model. And we'll call this new model C, and duplicate. All right, so here I have my duplicated model with our final parameter estimates. Next thing that we'll want to do is run a VPC via the PSN utility. So I can right click, PSN other, model diagnostics, VPC. You'll see our PSN command line arguments here. One thing that it's important to note, in earlier versions of PSN, the output here does not get extracted into a zip archive. In later versions, they automatically change that behavior where this output gets kind of zipped up. So we have this no zip argument here by default. And with all your PSN options, right, you can change this. If you go to PSN software integration, scroll down, visual predictive check, right, here's the initialization arguments for VPC. So maybe something else you'd want to add here is if you always want your prediction corrected, right, pred output in your VPC, then you can add dash pred core here. So I'll save and close. Let me go back to this PSN other, model diagnostics, VPC. Now you can see I have this pred core flag that's automatically in my args. So I'm going to hit run. And you'll see what happens when we do that. Should take about 10 seconds here. So keep in mind, we didn't change any PSN binning options. I think it was using the auto binning. The important, why we're using PSN here is the mechanism to create the observed and simulated data sets for the VPC results application, interactive application, because that's all that application needs. Your observed data set, simulated data set. It's based on the tidy VPC package. That's the underlying workhorse behind this application. So those who are familiar with tidy VPC package will kind of understand the two inputs that are required. All right, so I've created my VPC. You'll see I have this VPC folder that's attached to this model. With that, I can click this Analyze Results button. It's kind of the same button that we used for the Darwin Reporter, except now we're in the mod extension here, which means that we have different context for that button. All right, so I have a VPC attached to this model, which allows me to select this VPC results radio button, and I can hit run. All right, so now that's going to import the observed data set, the observed being the VPC original.mpctab.dta in the M1 folder that's inside this VPC directory that PSN created, and then the simulated being this VPC simulation.1.mpctab.dta inside that same M1 folder. And that brought up this interface. So you'll see we have some empty inputs here to populate in our yvar and xvar. So I can select yvar, toggle that to dv, xvar to time, and hit plot. So those are kind of the two minimum inputs you need to create your VPC. You'll see different customization options here below if we wanted to change different line types associated with the different quantiles, colors of those lines, the shaded region, different layout options around the, how the legend should be displayed, axis, free or fixed. If we wanted to facet the quantiles individually, we could. Different customization options for titles, subtitles, different text you may want to include. So all completely customizable. We wanted to keep the bin boundaries up there. You can leave this checked or hide them. If you wanted to have the lines go across the entire plot, select bin lines. So completely customizable. I'm just going to select Certara theme, toggle off bin lines. And just like in Darwin Reporter, we can use this tag button in the bottom right to go ahead and save this VPC and generate the underlying R code. So I'm going to tag this one. Another nice feature of this interface is you can always go interactive with your VPCs. So this uses converts the ggplot to plotly, and then allows you to kind of interactively explore the data and the different points accordingly. Here on the left, remember I added pred core flag in the PSN, which means that we do have a pred column in the output tables. So I can select this pred correction and select the prediction variable as pred. I wanted to create a PCVPC. Oops. Gotta plot it first. And here's our PCVPC. A lot of other different options available. If we wanted to stratify the VPC, we can select stratify, select the stratification column in the data. If we have BQL, we can censor on the variable in the data or particular value if you wanted to enter in the LLQ value manually. So a lot of flexibility here in this interface. Quantiles in terms of the quantile type to select. By default, the lower quantile is 5%, medium 50%, then 95% for the upper. Confidence levels set to 95% confidence level. And the controls, by default, we're using this PAM binning type, it's a partition around medioids with end bin set to 5. All this is completely customizable. If you wanted to select different binning types, you can see all the ones that we have available here. We'll change this to entile, maybe increase this to 7 bins, for example, if we want to capture some of the earlier time points here in the data. Plot, and here we have our tile. Let's see. Additionally, as an alternative to traditional binning methods, we have the binless method available in this interface, available in the underlying tidy VPC package. So you can select, toggle this from binning back to binless if you want to plot a binless VPC, which uses additive quantile regression in place of traditional binning techniques. And kind of the fit here is optimized by AIC. We have this corresponding lambda parameter that will dictate the smoothing of each one of these lines. And those can be manually specified as well if we uncheck optimize AIC, and you can select different smoothing values for each of the quantiles with higher values corresponding to smoother fits, essentially. All right, we can tag this binless. All right, quickly view all of our VPCs here in the tag tab, toggle between the different VPCs. You can see in the resulting code, right? This is kind of the data import where we read in the observed data, filter MDV equals to 0. Same thing for the simulated data. Here's our tidy VPC code where it's a chain of calls to observe, simulated, the binning method, and then the VPC stats to calculate the VPC statistics. And with that, you have a corresponding data frame of your VPC stats that within command line usage, we actually have a nice generic plot function that you can just plot this VPC directly. But ultimately, all this code is completely customizable with ggplot. So here you see kind of the raw plotting code under the hood, which is important, to expose all that as we're allowing users to add in all these additional customization options to their ggplot, however they'd like. So Finally, with those tagged VPCs, if I wanted to include them in a report, I would just drag them to the report output container. I could order them however I'd wish, select my different output extension. Here we have HTML selected, download report, and I'll also download the R Markdown just to show you how that kind of operates. Download R Markdown. Okay. So it's telling me the file was saved to Pirana scripts. That's the R Markdown. And let's go back to Pirana and just take a quick look at that. All right, so for our reports, I can go to the report tab, shiny, just like we did for Darwin Reporter, see our VPC report. So this is a just quick HTML report, that just has an overview of the different VPCs that we created. I also downloaded the R Markdown, so I can go to the Pirana scripts folder if I'd like. Files, I see this VPC report, RMD. Just double click that, open that in RStudio. And you can see I have the underlying R Markdown document available for editing here. So some nice, utilities in RStudio for visual editing of your R Markdown if you want to add in different headers, different text, subheader, name. All right, and then this is my body. And you can, render this report within our Markdown directly here in RStudio. If I wanted to render these individual chunks, just hit this play button, and you can see it's going to generate the resulting output here below. And if you wanted to re-render this into a complete report, then you would just use the knit button, knit to HTML, PDF, or Word. So some nice functionality, kind of efficiency between Pirana, RStudio workflows here. A lot of utilities to generate, the code, the underlying plots and tables that you would include in a report. All this, is code is kind of right at your fingertips, allows you to easily add this into, supplementary R Markdown documents, to integrate them into, a submission document for your final deliverable. So with that, I think I will close the webinar. I really appreciate everyone's engagement today. If you want to find out more information, certainly in the Pirana release, we have our Pirana user assistance. So that's always available here from help, user assistance, and that will take you to the Pirana homepage. We have examples for Darwin searches here in the Darwin search example zip file. So that would be a good place to get started. Information about how to use the different Shiny applications are, kind of linked here into Pirana, but there's also kind of standalone R package documentation for each one of these Shiny applications I presented today, such as Darwin Reporter and the VPC results. Right, and this is all available from certara.github.io/r-certara. Right, and we have different kind of usage details about how to work with each of these tools. All right, thank you, everyone. Have a wonderful day.